The first one, why we are setting up, the title is Improved Power Analysis Attack on Falcon, and the speaker is Xu Zhuanzhang. Please.
Okay. Thanks for the introduction. This is a paper about improved power analysis attack on Falcon. This is a joint work with Xiu Hanlin, Yang Yu, and Wei Jiawang. I'm Sto Zhang. In this work, we developed several key recovery attacks exploiting power leakage on Falcon. We give a new efficient key recovery using the half-Gaussian leakage with base simpler. We also gave the first stat channel analysis on Falcon, taking the sun leakage into account. Next, let's begin with some background. Falcon is one of the 3 post-quantum digital signatures to be standardized by NIST. Among the selected NIST signatures, Falcon has a good performance, especially it has the smallest bad ones, which is the public key size plus signature size. The Falcon is a lattice-based Hash-and-Sun signature schemes. So for the Hash-and-Sun paradigm, the Sun process is actually finding closed vectors in some lattice. In the early stage, the GGH and InterSun used the deterministic Bayes algorithm to find the closed vectors. The signature minus the hash message is always in a parallel pipe, which leaks the information about the secret key. So these algorithms are insecure. Finally, they were broken by the parallel piped learning attack. Then, in the GPV, they proposed a provable secure Hash-and-Sun framework. They run the hash message based on random Gaussian samplings instead of directly deterministic rounding. So the distribution of signatures is provably independent of the secret key. This, in fact, can be visualized as in this figure. The signature minus the hash message is in a sphere instead of in a parallel pipe. Finally, Falcon is an efficient instantiation of GPV framework by using the optimal intro trapdoor. Next, for the side channel analysis, with the PQC standardization and Magarisan way, security should be considered from both algorithmic and implementation aspect. The implementation security of Falcon is intricate. On the one hand, the signing relies on completed lattice Gaussian sampling. And on the other hand, the secret key is used in a rather opaque way. As a result of this, how to get the information about the secret key from the side channel leakage is also difficult to analyze. So we need to understand the connection between the leakage and secret key itself. As the target of the side channel attack is the Gaussian samplings in the Sun process of Falcon, so we next briefly introduce the Gaussian sampler in Falcon. There are 3 layers. The first layer is the FFO sampler, which is a run variant of KGPV sampler. In this sampler, the lattice Gaussian sampling is reduced to a series of one-dimensional integer Gaussian samplings. These integer Gaussian samplings have different standard deviations and centers. To deal with it, the sampler Z used the rejection sampling to get the Gaussian samples from with different parameters from a fixed half Gaussian sampling. Concretely, in this in the sampler Z, they first generate Z plus from with a half Gaussian distribution by calling base sampler, and then they compute Z with the random byte B. And finally, they output Z with a certain probability. Finally, the base sampler is implemented by a table-based approach. Now let's introduce the 2 leakage we used in our attack. The first one is a half Gaussian leakage. It is in the base sampler. Through the power consumptions of comparison in step 4, one can determine the value of the plus. And if the plus is equal to 0, the output of sample Z is 0 or 1. And the second leakage is the sun leakage. It's in two steps. The sun flip in step 3 and the computation of X in step 4. Through the powers of step 3 and step 4, one can determine the sun. Now let's move to our K-recovery algorithms. We first give the K-recovery algorithm by exploiting the half-Gaussian leakage. In the previous work, GMR, they first used the half-Gaussian leakage to attack the Falcon. They used this leakage to determine the output of sample Z. For example, if the Z0 plus is equal to 0, the signature S is always in this orange space. Then they reused the parallelepiped learning technique to recover the key. However, the attack is rather expensive. They need 10 million traces for directly key recovery. And with 1 million traces, they also need 1,000 CPU hours time to run the lattice reduction algorithms. In our work, we give cheaper key recovery algorithms. To recover the key, we first define the learning slice problem. And the slice it actually have same direction of the secret key, which can be seen in the vector B in this definition. We give new RSP algorithms. The idea is come from the geometric intuition that the projection of signatures in a slice on vector B0 is tended to be unusually short. And then our algorithm have two steps. We first learn the direction of the vector B, and then we estimate the vector's norm. In the first step, let's denote the metric B as the secret key of the Falcon, and the metric D is a corresponding metric, a corresponding orthogonal metric. Yes. In general, for the signatures of Falcon, the S, it can be seen follow the high-dimensional Gaussian distribution. And if the S is in a slice, the variance of Y0, the sigma prime is smaller than other coefficients. And the corresponding covariance metric have the following form. So the fact that the smallest eigenvalue sigma prime is unique, and its eigenvectors is the same direction of vector B. This allowed us to recover the direction through the spectral decomposition. Actually, this analysis can be understood as the principal component analysis, and the previous work can be understood as the interdependent component analysis. In the second step, the covariance of signatures also leaks the information about vector's norm. We can use the numerical method to estimate the norm through this intuition. And as for the experimental results, our key recovery algorithms significantly lowers the requirement of measurement and computation resources compared with the previous work. We only need 316,000 traces for directly key recovery, and 220,000 traces is inefficient for our algorithm to recover the key in 1/2 an hour. Next, we give the key recovery algorithms by exploiting the sun leakage. Actually, the sun leakage allowed us to determine whether a signature is in the orange half space or in this blue half space. Similarly, we also defined the learning half-space problems, and the direction of the half-space is the same as the secret key. We also give RSP algorithms. At a high level, our algorithms can be seen as a reduction from RSP to LSP. Our LSP have the following 3 steps. In the first step, we are aiming at learning a rough direction. And firstly, the coefficient of vector D0 is a half Gaussian, while others are full Gaussian. So the directions can also be learned through the spectral decomposition as well. And since the gap between the smallest eigenvalue and others not increases, and an accurate approximation requires more samples. So we can only learn a relatively rough direction instead of a very accurate one compared with the RSP algorithm. Actually, one can learn the directions through the expectation of samples, but this doesn't seem to improve the tech. In the step 2, to refine the accuracy, we attempt to amplify the condition number. We propose to use the rough direction V in the first step to classify all the samples into 2 sites. And in this figure, we only use the orange region, which can be seen on almost slice. Also, it's just almost slice. It contains enough information about the secret key to be catched by our LSP algorithm. So in the step 3, after applying our LSP algorithms, we can obtain a more accurate directions. For the experimental results, this attack is more efficient than the one using the half-Gaussian leakage. We can use the 117,000 traces for carrier carrier attack. Actually, we can use both leakage, both the sun leakage and half-Gaussian leakage, and then we will focus on a thinner slice, so our attack will be more efficient. We only need 45,000 traces for a carrier attack. To mitigate the sun leakage in the simple Z, we give a practical countermeasure, which have 2 components. The first one is for the direct leakage of B there. Our countermeasure encode B using 1 or 2 instead of 0 or 1. And concretely, we first generate a 4-byte uniform variable T, and then map it to the sum B using the lookup table. The first component is for the leakage amplified by the computation of Z and X. So we calculate all the values of Z and X and choosing the correct one with the value of B. Instead of computing 2x there, we can first compute 2 center C, C prime or 1 minus C prime, and then we can just compute x only once. As for the effective of our countermeasure, the SNR values of sun is much lower than the unprotected integer sampler. And we also conduct the template attack to calculate the classification accuracy. You can see in this figure with the increasing of the trees to make the template, the accuracy is almost 1/2. And while the classification accuracy for the unprotected sampler is almost 1. So finally, we give the conclusion. We provide an improved power analysis for Falcon. We give a new efficient query using the half-Gaussian leakage within the base simpler. And we also give a first side channel analysis on Falcon, taking the sun leakage into account. And the above attacks also works with imperfect classification. And finally, we also extend our attacks to the Mitaka, which is a variant of Falcon. With the post-quantum standardization, the megaris and V, the side-channel security of post-quantum schemes need more investigation. Thanks for your attention.
Thank you very much for the presentation. If you have any questions, please feel free to come to the microphone. While we are waiting, I can ask the first one, and if you do have, please feel free to line up. You mentioned about Mitaka, that your work can be applied to Mitaka as well, and could you please elaborate on how similar or differences, and how can you apply to that one?
Okay. Actually, there is also the sun leakage or the half-Gaussian leakage in Mitaka because Mitaka uses almost the same integer Gaussian samplings as the Falcon. But the Mitaka uses the different lattice Gaussian sampling compared with the Falcon. So the influence of this is that there is also a narrow on the secret key direction, but the condition number, as we also see, will be larger than will be smaller than in the Falcon. So we will need more traces to recover the key in the Mitaka.
Thank you. Any questions from the audience? Nope. Okay, so have you considered another variant of Falcon called Zalcon? Have you considered that one?
Okay, I think this Falcon is almost same with the Mitaka, so we didn't do experiment on it. Okay.
Thank you. Okay, no questions from the audience? So last one from me. So you mentioned about the cost of your algorithm, and I wonder if you consider online and offline phase to like split, do some pre-computation or something like that. Have you considered?
Sorry, I just
okay.
make
no problem. Okay, so I'll repeat my question again. So when you show the cost of your method, so I was wondering whether you consider online and offline phase. Like, can you do some pre-computation?
Okay, the online offline in the Mitaka, we only consider the online samples of the Mitaka, and the offline didn't use the integer Gaussian sampling, so it's not the target of the side channel analysis.
Okay. If there's no questions from the audience, so let's thank the speaker again. Let's move to our next presentation for this session. So while setting up the slides, so I can introduce, the talk will be on effective and efficient masking with low noise using small Meson prime ciphers. And speakers will be Loic Masur and Torben Moos.
Yes. Thanks for the introduction, and thanks for attending this last session of the day. So I will give the first half of the talk, and I will let Torben give the second half. So we are talking about sidechain analysis. So to recall a bit of context, in classical black box script analysis, an adversary is aimed to recover some information about the secret key based on some pairs of input and output text. But cryptographic algorithms don't run on paper or on blackboard, they run on physical devices, which means that for any intermediate computations that is embedded into your device, you may leak some physical measurements like the power consumption, the electromagnetic emanations, the runtime, or the acoustics. And another dimension of this problem is that these intermediate computations only deal with small chunks of data, which means that we can recover the secret in a divide and conquer approach up to the point that the complexity of such analysis can be linearized compared to a black box. That's why this is a threat that needs to be taken into account. But thankfully, we do know some ways to protect implementations against such an analysis, such as masking. Masking is the most well-known countermeasure, and if you don't really know a bit of such analysis, think of masking as MPC, multi-party computation on silicon. More concretely, we will apply to each intermediate sensitive data processed by the implementation a linear secret sharing over a given finite field, and you may use the finite field the most appropriate with respect to the specification. So for example, if you run an AES, you could choose F here as the AES field. And the idea is that instead of having a secret data here denoted by Y leaking directly, a physical function, you will have only the shares of your secret sharing that we will leak. And why is this interesting from a security perspective? Is that we are often known that masking amplifies noise. And what do I mean here is that, for example, let's take a simulation where we assume that each share will leak its Hamming weight, so the sum of its bits, plus a given Gaussian noise independent. And what we can see here is that we can measure the level of mutual information giving the overall secret, so the Y here, and the overall trace here measured at the oscilloscope. And what we can, and this is for different ranges of the Gaussian noise that is sampled, and for different numbers of shares, 2 to 6. And what we can see here is that for a given amount of noise, we have a constant gap between each curve, which means that we have an exponential security with respect to the number of shares D, which is our security parameter. So here, masking works well. But as I said, masking amplifies noise, which means that if I don't have enough noise, I cannot amplify it. And this is what I will show you here, exactly. On this left part of the graph, I have an issue, because here we can see that I no longer have a constant gap between each curves. This happens when I don't have enough noise, so I'm on the left part of the graph. And why does this happen? Is that because we can see here that the secret always leaks at least one bit of information, regardless of the number of shares. And why is this happening? So to understand that, let's take a small explanation. If I assume that now each of my shares leak only the Hamming weight and without any Gaussian noise, then I can recover one bit of the secret as follows. I can just use this small formula. That means that the Hamming weight of the XOR of several bytes, for example, is the sum of the Hamming weight minus 2 times a term that we don't care about. What I only care about is that the parity of my overall secret is stable by the XOR addition, because the parity of the left-hand side is equal to the parity of the right-hand side, namely the sum of my leakage. So we say that parity is stable by the operation, and in a more algebraic manner, this means that this sets of parity of odd or even Hamming weight is a subgroup of my finite field here, my Galois field f of 2 to the n. Okay, let's take an example to be more concrete. Let's assume that I first have one share, so no masking at all, and I can observe at the oscilloscope that my secret has an even Hamming weight. Then I can translate it as I can translate my physical observation as probability distribution here over 8 values if I assume to have a 3-bit S-box, for example, a 3-bit block cipher, with 4 key candidates remaining, denoted by the red square here, whereas I can eliminate directly 4 other candidates in white squares. But now, if I have 2 shares, I'm assumed to have a noise amplified, but I can see here that when I compute the convolution product of my probability distribution, which is how we translate the secret sharing, we can see that we no longer have noise amplification because we have still the same number of remaining key candidates for the overall secret. And here, if I add another share, I have the same problem. Even if I increase the number of shares, I still have the same number of candidates. So we have a shift from one subgroup to another coset of this subgroup. Okay, and as a corollary, the parallelism cannot help either to fix this issue. Okay, so we had a counterexample, and now I would like to know whether there exists a general condition, sufficient and necessary condition to fix this problem. And hopefully there is. We have a nice paper from 2016 by Dziembowski, Faust, and Skorsky that says that the masking countermeasure, in a nutshell, is sound if and only if the support of my probability distributions of the shares given their corresponding leakage is not supported, whose support is not contained in any non-trivial subgroup or coset. And so this is a rather abstract condition. Let's have two solutions to fit this condition. Either we make sure that we leak less than 1 bit per share, because in that case, we know that the support is at least half the size of the finite field, which means that it is bigger than any non-trivial subgroup or any non-trivial coset. But the problem is that this assumption is leakage dependent, which is not always verified, as we have seen. The other solution is to work with a finite field without any non-trivial subgroup, which means that we work in prime fields. And this and there, we don't need any assumption on the leakage. And that's what we propose here. So instead of working in a Galois field in green, we propose to work in a prime field in red. Okay, and now I let the floor to Torben.
Thank you very much. So now that we have seen that there is some interest from a theoretical and an information theoretic point of view in using this masking in prime fields, the question is, how do we use that? How can we leverage that to effectively and efficiently protect crypto implementations? And the answer to that question is a bit tricky, because ideally we would need algorithms that work in certain types of prime fields, namely implementation-friendly primes, for example, small Mersenne prime fields, and that only use simple arithmetic operations so that we can apply very efficient arithmetic masking. And we have looked around the literature. Apparently there are no schemes that really fit all the requirements that we want to have. So what we decided to do is building one our own. And what we did is, what we developed is this AES prime. AES prime is an AES-like toy cipher which is adapted for prime field masking. We copied as much from the standard AES as we could, so like the whole structure and the order of operations, but adapted all the operations so that they work based on arithmetic addition and multiplication modulo a prime. Now the prime that we have chosen for efficiency reasons is the Mersenne prime 2 to the 7 minus 1, because we can do very efficient modulo reduction. The S-box is based on the smallest power map and the smallest affine mapping that gives us a bijection without fixed points. It's given on the bottom left. The mixed columns operation is a 4 times 4 MDS matrix, also equivalently to the AES, but of course a different matrix because we will work in a different field. The interesting part is that all the elements are powers of 2, and if I multiply a value by a power of 2 modulo a Mersenne prime, that's just a rotation of the bits, so we have some nice efficiency there. And we analyzed this toy cipher and borrowed elements from the Hades design strategy and also from standard AES cryptanalysis. And our conclusion is that with 14 rounds, we achieve 112-bit of security, 112-bit because we have this 112-bit state and key, which is 7 times 16 elements. That is because the Mersenne prime 2 to the 7 minus 1 is the closest to the field that AES is operating in. Now, whenever you tell engineers that you want to work in prime fields and they have to do arithmetic addition with carry propagation, modulo a prime, they think, okay, this is going to be way more complex than just doing a simple XOR. And this slide is just trying to say that on like standard 32-bit microcontrollers, we can actually do that very efficiently because we have a simple addition operation. So the C code on the left translates to the ARM assembly code on the right, and that executes constant time in 3 cycles, and you can even do multiple additions before doing the reduction, which runs in 2 cycles. Of course, we have some slight overhead here compared to an XOR, which would be just a single cycle. However, in the multiplication case, we can execute that in 5 cycles, also constant time, and there, the equivalent for the Galois field multiplication in a binary field would actually, for operands up to 16 bits, which we can do here, would take more than 100 cycles because we have no native instructions for multiplications in these fields. For arithmetic multiplication, we have this. In hardware, it looks similar, so I don't want to go into too much detail, but essentially we can use the native operators for addition and multiplication and then craft the modulo reduction trick for Mersenne primes. And now I want to come to one of our software case studies. So we have some case studies in our paper. I only want to detail one of them because of time constraints. And that one I have chosen because it is like the most fair comparison. It doesn't depend on the arithmetic differences that you have between those fields, at least not from the implementation point of view. And we have used a naive implementation of this masked x to the 5 plus 2 operation, which is the S-box of the AES prime. So in both fields, we use this operation and we implement it with 3 consecutive ISW multiplications, so the standard masked multiplier. And it's neither the most efficient implementation for each of those fields, but we needed something where the operation principle is exactly the same so that we can compare it. And what we see here on the top row is the sample traces, on the left for the binary field, on the right for the prime field, and in the bottom we see signal-to-noise ratio figures for the first input share. So what this slide is supposed to tell you is that it looks very similar. So the measurements look very similar. We have a few more cycles in the prime case. And the SNR is like slightly higher, but like by no significant factor. And now we want to see what kind of security gain we get when we pay like very similar amounts of resources to implement this. And for that, we did like a kind of worst case analysis, namely a horizontal Saska attack on implementations from 2 shares up to 6 shares on an ARM Cortex M3 microcontroller. And the Saska attack is a profiled analytical attack where we first profile all the intermediate values in the multiplication chains and try to extract information about them individually, combine that information using a factor graph and belief propagation to get a probability distribution on the secret value. With that, we can estimate the guessing entropy and the key rank, which is what you see plotted here in the bottom of the figure over the number of traces. And the x-axis is a logarithmic scale, so like small differences on this scale are already severe differences in the security. And what we observe is that up to 6 shares, all the implementations I can break with 60 attack traces. So I have the same number of profiling traces for both of them, but only 60 attack traces are enough to extract all the information to break the implementation. On the other hand, for like the same implementation just in the binary field, because it's harder to combine the information into the secret, we need up to 10,000 traces. Now I want to advertise a follow-up of our work, which is already published at Teachers this year, issue 2. It's called Prime Field Masking in Hardware and its Soundness Against Low Noise Attacks. The work is way more hardware-focused than this one. It introduces new arbitrary order Piney gadgets for secure squaring, because squaring in prime fields is nonlinear, so we need some gadgets for that. And it also has optimized constructions of masking this AES prime S-box and an evaluation between the standard AES and the AES prime, and there you find the links for the GitHub repo of our code and the paper. Now to conclude the talk, we believe that additive masking in small and implementation-friendly prime fields is quite promising for physically secure cryptography, and that is because we can mask securely without the need to guarantee a notable amount of noise, which is really important, especially on these software devices. What we demonstrated is that the security advantages over Boolean masking can reach multiple orders of magnitude, right? You saw the difference between 10,000 traces and 60 traces. And what we already observe is that you even get advantages at high noise scenarios and against fault attacks. That has to be analyzed in more detail, but it's quite promising for future applications of this. Now, the last thing is just a call for symmetric crypto people. If you're searching for interesting things to work on, we really need like more efficient ciphers than this AES prime for this kind of problem to explore the design space, to explore the interest of this design space even deeper and see whether we can do like really efficient symmetric crypto that operates optimized for prime masking. Thank you very much.
Thank you very much for the talk. Are there any questions from the audience? Can you turn it on?
Okay. Thank you. Thank you very much for this nice talk. So one question, do you need arithmetic to Boolean conversion or the other way around at some point in your specific ciphers?
No, that's a good question, because at the point where we would do that and convert to like the Boolean encodings, we have already lost, because then we lose all the gain, right? Because then if I measure, I don't have this noise amplification if I have too low noise on the shares, and that is a problem. So never convert, always stay on prime field with like these ciphers.
Okay, thank you.
Hi. You have not settled on any prime yet, right? If a symmetric cryptographer were to decide to look into this area, that's something they can pick at this stage.
Exactly.
Okay.
So our suggestion is to use these small Mersenne primes, because in like, for small exponents we have quite many. I think for 3, 5, 7, 13, 17, 19, 31. So it should be smaller than 32 probably, but you can choose any prime where you can do efficient modulo reduction in constant time.
And what would you expect the impact of the size of the prime to be? Like, would a bigger prime be better for you? Would a smaller prime be better for you?
That's a great question. We have details on that in the paper. So actually the constant gaps that you see in these information theoretic plots, they increase significantly with the field size. So larger primes are actually better for the security. Of course, in hardware, they are especially worse for performance.
Okay. Thanks.
Yeah, thank you for the talk. Did you check whether this masking can also work for PQC scheme? Because PQC scheme, we also have quite friendly prime. Do you check whether it works?
We didn't check that yet, but yeah, that's an important thing for the future.
Any more questions from the audience? If not, I would like to ask one question. So you mentioned about implementation-friendly prime, and in your paper you look at small Mersenne prime, but are there any particular criteria for implementation-friendly? For example, can it be pseudo-Mersenne prime or a different kind of prime, or are there any criteria that you're looking at?
Yeah, all these like implementation-friendly primes like Mersenne, pseudo-Mersenne, generalized Mersenne, Montgomery-friendly, they are all fine, but none of them are more efficient than Mersenne primes, and you only really need them if you don't have a Mersenne prime of the size that you want. Then you can use pseudo-Mersenne primes, for example. It will not affect the security. So security analysis works for any prime, even implementation-unfriendly primes, but of course then we have not the efficiencies that we would like to have.
Okay, thank you very much. Let's thank the speaker again. Okay, last talk for today and for this session. And the title of the paper is One-Hot Conversion Towards Faster Table-Based A to B Conversion. And the speaker will be Jan-Peter Danvers. Please.
Yes. Thank you for the introduction, and thank you for staying for the last talk. So this talk is also about masking A to B conversion, so I will quickly give an overview, but a lot has already been covered, so I will go quickly at the start. So if we talk about masking, we talk about side channel attacks. So what are side channel attacks? These are attacks where we don't attack the mathematics of a scheme, of a cryptographic scheme, but where we try to use like measurements, try to use measurements while computing on this device to extract, for example, power consumption or electromagnetic radiation, and from that get the secret information that we want. And so masking is a way to protect against these side channel attacks. So the idea of masking, to repeat, is that we have a secret, we're computing on this secret, and we don't want this secret to leak, so we will split this secret into several what we call shares. So we will have several shares, and the idea is that an adversary needs to find all of the shares or get information on all of the shares in order to reconstruct the secret. And as long as the adversary has no information on all of the shares, he will not be able to find any information about the secret. So there's different ways to do this sharing. One way is that you could do Boolean sharing. This is essentially a one-time padding. So what you do is you split into shares, and the way to combine these shares is to take an XOR of this share. XOR of all these shares, that will be the secret. Another way to do this is arithmetic sharing. So the arithmetic sharing, the same ID, we divide it into these different shares, but to combine into the secret, you have to do an addition modulo sum q. Okay? Now, why do we have different ways of masking? If we look at an implementation, and as an example, I took Kyber, which is the NIST encryption standard, or the new post-quantum encryption standard. So if you look at this, what you'll see is that some operations you actually want to do in the arithmetic domain. So typically, arithmetic operations, multiplication, subtraction, you want to do in the arithmetic domain, while hashing or some Boolean operations like comparison, you typically want to do in the Boolean domain, right? So that's why we use these two domains. The annoying thing is that we now have to convert from one domain to the other domain. And so we need conversions from the arithmetic to the Boolean domain and vice versa. But we will talk in this talk, we will talk about arithmetic to Boolean conversion. Also something to note is that when I talk about first order, I mean that we have two shares. And if we talk about higher order, we will have more shares, more security, but also more cost, of course. So the goal of this presentation, we want to make A to B conversions. And actually, this already exists. Right? And we can divide this into two main families of schemes. The first one is circuit-based schemes. The main idea, very roughly, is that you write down a circuit and then you protect each of the gates of this circuit with a masked equivalent. And that's how you construct your A to B conversion. The second one is table-based. What do? You make a masked table, and then for each input share, you shuffle the table and you do a remasking, and then in the end, you can do a final lookup with the last share, and you will get your information. So that's the two main IDs. And if we look at these, so there's references there for if you're interested. If you look at this, the circuit base scale really well to higher order. At least there's a nice scaling there. While the table-based are really efficient in first order, but at the moment, very inefficient in higher order. At least this 2 years ago, this paper came out on the slide by Coron et al. And it's very interesting, but it's still quite inefficient for higher orders. So in this talk, I want to talk about this one-hot encoding. So one-hot encoding is an improvement of table-based methods. And what we do is, instead of using a table, we will use a one-hot encoding of our secret. So imagine our secret is 3. What we'll do is we'll have an array of all zeros, and we will have 1, 1 in this array, and this will be at the 3rd position. We start counting as 0, right? So one-hot encoding, we have an array, all zeros, there will be 1, 1 in the array at the position of the secret. Now, of course, we have to protect this. So what we do is we do a masking of this element. So we will have this array Boolean masked. And now to show that this is a good intermediate representation, in this presentation we will first do this arithmetic to intermediate to the one-hot encoding, and then we will show that you can go from the one-hot encoding to the Boolean domain. Well, actually, we'll first go from the one-hot encoding to the Boolean domain. So how do we do this? it's actually a shairwise operation. So you take this, the 0th position, you multiply it by 0. You take the first position, you multiply it by 1, and so on. And then you XOR everything together. And so because you do it shairewise, you'll get a number of shares. And this is the Boolean conversion that you actually need. It's the Boolean representation. So if you combine the shares, everything will fall away. That corresponds to a 0 in the one-hot encoding. And the place where the 1 is, this place will stay, and we will have our value. Right? So we can easily go from the one-hot encoding to the Boolean domain. The nice thing is that all these operations are sharewise, so it's easy to protect. And you can actually implement this more efficiently than shown here. We can even apply any function, right? So we're not limited by the unity function. You can just, instead of multiplying by the position, we can multiply by a function of the position, and this, for nearly free, gives us a conversion with any function. So how do we go from the arithmetic domain to the one-hot domain? Well, what we do is we use ideas from the paper by Caron 2 years ago in chess, where they use a one-bit table-based method. The idea is that we start from an encoding of 0. And now, if we want to add an arithmetic share, we can rotate the encoding. So if you have an encoding of 0, the 1 will be at position 0. And now if we rotate this encoding by, let's say, 10 positions, then we will now have an encoding of 10. So essentially what we did is we added 10 to this table. And so this way we can add arithmetic shares. So imagine we start with an encoding of 0. In this example, we add 10. So we rotate the whole encoding by 10 positions. Then we want to add 9, so we have to rotate it again with 9 positions, and we will get an encoding of the secret. Of course, you have to take into account the modular reduction, but that's because we have the rotation operation, and you have to do remasking, but more details about that in the paper. So in the end, what we have is a two-step procedure where we do this rotation operation to include all of the arithmetic shares, and then this Boolean sharewise operation to get out the Boolean shares. However, as you can see, this will not scale well. If we want to have big numbers, then we have to have a very big one-hot intermediate representation. So how do we scale this up? Well, what we do is we will divide the input into input arithmetic shares into chunks of n bits. And we will process these n bits all individually. So we'll start with the, let's say, 2 least significant bits in this example, and then we'll go to the next 2 bits and the next 2 bits. And we can do this. The only thing that you need to take into account is the carries, because there will be carries propagating from the least significant bits to the more significant bits. So how do we do carry propagation? The main idea is essentially the same. So we add these arithmetic shares one by one by doing a rotation. But instead of doing a rotation, we're now going to just shift. So we're never going to do the rotation, which is actually the modular operation. And now, depending on how much we have shifted, we can actually read out the carry. So if we've shifted between 0 and 4 positions, then we know that there's no carry. In this example, Q is 4, right? If we shifted between 5 and 8 positions, then we know the carry is 1, and so on. So what we do is we just take the first 4 positions, we XOR them together, or we add them together, which is an XOR, and we put them at position 0. Then we take the next 4 positions, this corresponds to carry 1, and we add them at position 1. And if we do this, we will get a representation of our carry in the one-hot encoding. And this representation of our carry we can use in the next iteration to start with. So we will not start with an encoding of 0, but we will start with an encoding of our carry. And now we add our arithmetic shares. And in this way, we automatically take into account these carries. So if we scale the A to B, we have 3 components instead of 2. So we will have the arithmetic to one-hot encoding, where we now don't do a rotation, but a shift operation. We'll have the one-hot to Boolean, which is still a sharewise operation. And then we'll have the carry propagation, which is also a sharewise operation. Quickly, before we go to the results, I want to say that in the paper, we also look at 1-bit output functions. So in this, we have arithmetic inputs, which are larger, but we have specifically 1-bit output. So these functions are really interesting for post-quantum crypto. For example, if you want to do the decoding operation, it's essentially a most significant bit extraction, so it's a one-bit function. There is ciphertext validation in the evode transformation that you need to do. Essentially, all of the A to B operations in post-quantum crypto are one-bit functions. And so for these functions, what we can do is we can simplify the whole circuit. Just to give an example, there's more details in the paper. We want to check if a masked value is 0. So what we do is we do the first step as before. So we do this shift operation with all the arithmetic shares. But now what we do is we only copy the position that corresponds to the 0. So we will only, in each chunk of carry, we'll only copy the zeroth position. This means that if the 1 is in the 0th position, then our condition is fulfilled and we will propagate the 1. But if the 1 is not in the 0th position, the 1 will disappear from our one-hot encoding and we will have an encoding of 0. So we will compute on zeros, we will keep on computing on zeros, and in the end, we will just have an encoding of zeros, and we know that at least one of the conditions was not fulfilled. So we can really optimize this method for functions in post-quantum cryptography, or in maybe other fields of crypto. So what are the results? We can compare our methods to the table-based methods, and we can compare our methods to the other family, which is the Boolean circuit-based methods. So if we compare to the table-based method presented 2 years ago, we can see that we have a speed of about 16 times. So our method is 16 times faster. Note that both implementations are not optimized. So neither theirs, I think, and my implementation is optimized, but just to show, to get a rough idea. If we compare to the Boolean circuit-based methods, we're slightly faster if we ignore randomness sampling. We're also comparing to a more optimized implementation. If we, on the other hand, look at randomness cost, again, compared to the table-based methods, we are like a factor 14, we need a factor 14 less randomness, so that's good. But we need a factor of 3 more randomness than the most optimized Boolean circuit-based methods. So this is something that we need to work on if we want to improve the table-based methods, or both methods actually. If then you look at the cycle cost with randomness sampling, and this is a non-optimized thing where we have stalls because we do not spread out the randomness sampling in the programming, we'll see that our implementation is actually slower. But if somebody can actually implement this while spreading out this sampling, this might actually be faster. So that's a call to you to maybe optimize this. So just for the comparison with table-based methods, I think for the A to B conversion at least, the table-based methods are, the one-hot encoding is faster, needs less randomness, with the caveat that these are proof-of-concept implementations, but still there is a definite speed up. For the circuit-based methods, it's a bit more iffy, like we are faster when we disregard this randomness, but if we have this randomness with our non-optimized implementation, we are slower and we need more randomness. So does that mean that circuit-based methods are better still, because less randomness and the speed up is like, not necessarily. Why do I say that? I think we need more research in this field. Higher order circuit-based methods are more mature. They exist for a longer time, and there's optimized methods available. For the table-based methods, there's no optimized implementations available yet. I would not call my implementation optimized. So, and so we already, the one-hot encoding already caught up in speed, but the focus point is really randomness reduction. So this is really something to look at in the future. So what is future work? Well, this randomness reduction. So I've talked about it, and I think this is the case for both the table-based methods as the circuit-based methods. We need to look at, we've disregarded randomness use for a long time, and I think we need to look at how to reduce this randomness, how to maybe reuse randomness in the future if we really want to make efficient implementations. If somebody can look at an optimized implementation, would be nice. But also it would be interesting to look at first-order optimization. So in our paper, we mostly looked at higher orders, and table-based methods are very efficient in first order. Maybe if you take the one-hot encoding and try to implement it first order, or try to make an optimized first order implementation, you get some nice results. And then a more out there idea is the fact that, as already nicely introduced in the previous talk, leakage is typically Hamming weight based. Now, the one hot encoding will always have a constant Hamming weight. So maybe because of this, intermediate representation, there might be some way to quantify this and to reduce the security level that you need there, because there is an inherent resilience to some kind of faults. But that's really future research. So with that, I end my talk, and I'm happy to take any questions.
Thank you very much for the nice presentation. Any questions from the audience? Please come to the microphone, please. Can you please come to the microphone in the middle?
I didn't see any evaluation on the security level of your implementation.
Yeah, so we did not do side channel testing.
Yeah.
So we have security proof.
Yeah, I saw that.
And you can see, like, for a certain order, but we did not do any, also the implementation, please do not take it and put it in a real product, because we did not do any, I mean, this is not a secure, this is really proof of concept implementation. We also did not do any side channel testing.
Yeah, but are you going to do that? Because it's the point, right?
I'm not planning to do that. So, I mean, that's why I'm also putting all my ideas here. This is for people to continue work on. I'm at the moment not looking at this.
Okay. Yeah. Thank you.
If you say that you're slower if the randomness is sampled on the Cortex M4, then you're using the internal RNGs?
Yes, yes.
So could you imagine that you implement some RNG yourself, which is more efficient, still sufficiently secure for the demands of masking schemes, that you're then better? I think the cost of randomness is still not well understood.
Yeah. There's different things. That's why I wanted to report it separately, because it's kind of like, I wanted to report it without, because if you have like whatever, if you have the randomness, you can use it. But I also wanted to report it with, because I want to have this discussion about randomness, because I think it has not been addressed enough, especially, I mean, it's more mature discussion in the symmetry key field, but it's less in the post-quantum field. So it's more kind of like trying to put it out there as, I think, an interesting topic. I think there's tricks. If you look at the code, for example, the randomness sampling is in this first procedure, which is the arithmetic to one hot encoding. So one thing you could do is spread this out in time, or use other ways to get the randomness. Definitely something that I didn't look at, but that are interesting to consider. I mean, there's different possibilities there. I think the first thing, if you really want to optimize, is really just spreading out the calls to the random number generator, that's a difficult word, in spreading it out in time. But also, yeah, other options are definitely possible.
Okay, thanks.
Are there any more questions from the audience? I have one question. So in your talk, you mentioned about A to B conversion. So I wonder if you consider B to A conversion as well.
Yeah, so that's also a very interesting question. So B2A conversion, so there's two ways you could approach this. You could try to really natively make a B2A conversion out of this. Probably you'll have to have an intermediate representation that is arithmetically masked. But with carries and things, I would not immediately know how to do this. The nice thing about the Boolean masking is that you can kind of do the rotation. This is more difficult with the arithmetic masking. But yeah, why not? The other way is that you can use the A to B conversion actually to create a B to A conversion with techniques that do exist. So that's definitely an option that you can do. And then trying to build natively, like really adapt this to natively support B2A, I think cool project for something to look at, so for somebody to look at. So.
Okay, thank you. We are right on time, so let's thank the speaker again. So this is the end of this session and for the first day. So as Damian announced this morning, there's no official dinner for tonight, and tomorrow we will start at 9 a.m. Let's thank all the speakers for this session.